What's up? I'm Vin, and today I want to go over sigma notation. So first we're going to have the definition of a series, which is a sum of a given sequence of terms. And sigma notation, when I draw sigma, I think of drawing a sideways capital M. And let's say I look at the series from k equals 1 to 5 of k squared. So what each of these terms mean, this term here we call the summand. Kind of like if we had a radical, we call this the radicand, but for summations we call this a summand. And then the number on bottom here tells us where to start. And the number on top tells us where to stop. So when we want to evaluate this, we start at 1, and we plug in k equals 1 to get 1 squared. We plug in k equals 2, and that'll give us 2 to the second power. And then we plug in 3, 4, and 5, but we stop at 5 because 5 is the number at the top of our sigma here. And now this series, we're going to add all this stuff together. So sigma is often interchangeable with summation. This just tells you to add up all the k squared terms from k equals 1 to k equals 5. So now we just have to simplify this. So it's going to give us 1 plus 4 plus 9 plus 16 plus 25. And then if we add a few of these together, like I look at these three together make 14. And then 14 plus 16 is 30. And then I have 30 plus 25. Which is equal to 55. So this is going to be the value for our first series. So let's look at a few more examples here. Let's say we have the series from j equals 3 to 5 of 1 over j. So we're going to plug in j equals 3, and then we're going to plug in j equals 4, and we're going to go up to j equals 5. So this is just going to be 3 terms that we have to add together. And then we just have to use what we know about fractions. A common denominator here we could use is we could use 60. So what we could do is, to get to 60, we would multiply the first fraction by 20 over 20, and that would give us 1 times 20 over 3 times 20, which is 20 over 60. The next one we can multiply by 15 over 15, and we get 1 times 15 is 15, and 4 times 15 is 60. Plus, in the last fraction, multiply by 12 over 12, and we'll get 12 over 60. So now we just got to add this stuff together. These two make 35, and 35 plus 12 is 47. So this is going to be 47 over 60. Now we could look at another example here. Let's say this time around we look at the series from k equals 1 to 6. And let's say this time the summand is just the number 2. Now sometimes the examples, the more simple they are, the more confusing it is. But the way I've come to understand these is we're starting at k equals 1, and then we have k equals 2, 3, 4, 5, and 6. Okay, so we'll just write the last one out here. But now what I'm going to do is for each term, the summand is just 2. So I'm going to put a 2 for each of these values of k here. So now we just add all this together. And how many 2's do we have? There are 6 of them. So 2 times 6 would just give us 12. Now, a better thought process for something like this would be that you know you have to multiply 2 by however many terms there are. But from 1 to 6, there would be, in a sense, 6 minus 1 plus 1, or there would be 6 terms for us to consider. It's a little bit deceiving. People just think 6 minus 1 is 5, so there'll be 5 of them, but it's inclusive, so that tells us to add 1 back on. So this is going to work out to 12. So let's look at this next question here. We want to write each sum using sigma notation. So we have our symbol here for sigma, and I look at what's changing and what's staying the same. So the base is changing, so that we could put a letter k for, and the exponent is remaining 3. Now we just have to think here, the first term in our sum is 1 to the third, so that would be the result of plugging in k equals 1, and this thing stops at k equals 6. So this would represent our series here. Now we'll look at another example where, let's say this time I have the sum of these square roots. So what I notice here is we're going to set this equal to the series. This time around the square root is staying the same, but the term inside the square root, the radicand here, is increasing by 1 each time. So this would just give me square root of k. But the difference is that I have to be careful. I can't start at k equals 1 for this type of summand. I'm going to start at k equals 3 because the first term in the sum is square root 3, and the last one is 77. If you really want to start at k equals 1, just know there are more than one answer to questions like this. So what you could do is, if you want to start at k equals 1, you just have to think a little bit more about what would go under the radical. And if I have to start at square root 3, I would need square root of k plus 2, because when we plug in 1, we'd have 1 plus 2 is 3 under there. And then we just have to be careful. The last thing would be at k equals 75, because 75 plus 2 would give us the 77. So just know this is also a correct answer, but this one here is probably the most obvious that pops up. So let's expand a few more series, but now we'll make them a little bit more complicated. So for something like this, I'm replacing the letter I twice. So I'm going to have 1 times 2 to the first, since we're starting at I equals 1. And then we're going to plug in I equals 2, which would give us 2 times 2 to the second, like this. And then we're going to stop at I equals 3, but when we plug in 3, we're going to have 3 times 2 to the third power. So now we just have to use order of operations and be careful simplifying. 1 times 2 gives us 2. This would give us 2 to the third power, which is 8. And this would give us, order of operations, we do the exponent first, so we'd have 8 times 3 is 24. And if we add all this up, 2 plus 8 is 10, plus 24 is 34. So this would be our solution to the next question. Now for something like this one here is a little bit tricky to deal with, but what I'm going to do is look for a pattern. So I would see when we plug in I equals 1, I'd have 1 plus negative 1 to the I equals 1, like this. But I notice this is going to give me 1 plus negative 1, which is going to work out to 0. But then the next thing I would have 1 plus negative 1 to the I equals 2, which would give me 1 plus 1, which is equal to 2. So notice I get 0 plus 2, and then after this one you might notice the pattern. So what I have this time, I would have 1 plus negative 1, and we did I equals 1, I equals 2, now it's I equals 3. And you can see here, this is going to give us 1 plus negative 1 to the third is negative 1, so 1 minus 1 is 0. So here's the pattern. This is our first, second, third. The fourth one, we have 0, 2, 0, 2. So I'm not even going to bother setting it up like this because the pattern is now obvious. So this is the first, second, third, fourth, fifth, sixth, seventh, eighth. And I would just count it out like this. And I just say how many 2's do we have? We have 2, 4, 6, 8. So these add up to 8. We have 2 times 4. This is our solution to the next example. So now we'll just end with 2 tricky ones here. So let's say I look at these 2 examples, and we'll do them separate here. But what I want to find is a series representation of this sum. So here, what I notice is, well, we're going to have our summation, but I have a 1 on top because all these numerators are equal to 1. And then on bottom, I have a number with the number that comes immediately after it. So I have consecutive numbers in each of these denominators. So if I make the bottom k to represent the first thing, the next thing is 1 more than that, so it'll be k plus 1. But now I just have to think about where do we start. We start at 1 times 2. So that would give us k equals 1. And then we just have to think about, well, where do we stop? We would stop at k equals 999. And now I would just do like a little mental checklist here to make sure that this is correct. But notice when I plug in 1, I get 1 over 1 times 1 plus 1, which is 1 over 1 times 2, which checks out. And when we plug in 999, we get 999 times 999 plus 1, which gives us that last term. So this one definitely checks out. So let's take a look at this last question here. This one is definitely the most complicated. So one thing I noticed with this series is that the terms alternate. So they alternate in sign. And then another thing that I notice here is that the coefficient of x is 1 more than the exponent. So the coefficient of x is 1 more. So when I'm putting the series together, these are some of the things that I look for, and that helps me when I recognize the pattern. It helps me set up the series correctly. So how do I take care of the fact that this thing alternates? Well, that tells me to throw in a negative 1 to some power k here. So I have negative 1 to the k, and if I need to adjust this, I can. Because sometimes you have to make little tweaks to make sure that all the terms match. Now, another thing that pops out is that this thing starts positive. So when I decide ultimately what's the perfect k equals to start at, I have to make sure that I'm starting at a positive and not a negative. So now what I have is I have my coefficient and I have my x to the k power. So we'll just make that a little bit neater. So we have x to the k power. But my coefficient is 1 more than the exponent. So whatever my exponent is, let's say 99, I would do 99 plus 1 to get the 100 in front. But now we just have to make sure that we put in an appropriate k value, because the k equals that we're starting at has to make this thing start positive. And also the first power of x is technically x to the 0. So the first k value to try right now is k equals 0. And notice what it does. Negative 1 to the 0 is positive 1, which makes this thing positive. And then x to the 0 is 1. And then if I have 0 plus 1, that makes this 1. So k equals 0 looks like a good start. But then I think about what's the highest power of x that we end at, and that's 99. So this series here would actually capture the entire sum that we started with. And once again, just to make sure that I'm correct, I do a little mental check. I plug in k equals 0, and I plug in k equals 99. And notice negative 1 to the 99. 99 is odd, so that would make this last term negative. And then 99 plus 1 is 100, x to the 99. So this thing definitely checks out. Okay, well, this is going to conclude this video on sigma notation. If this video was helpful, please like and subscribe. It really helps me grow the channel. And if you got any requests, just leave the topics you want me to cover in the comment section below. And thanks for watching.